So now that we've moved into molecular geometry, that's where when we have lone pairs, the name is going to change and it matters. Now, if you look at this molecule and we're only looking at the central atom, this one right here, it doesn't have any lone pairs. It's got all bonds. We are not asking about these external atom lone pairs, right? We are only looking at the central atom and it has only bonds. So in that case, since there are no lone pairs, we don't have to change anything about our theory or the molecular geometry or anything. So this one is still called trigonal bipyramidal. And then right here, the molecular geometry, this is where things start to change because I've got that lone pair right there on that central atom. So the name of this shape where you have the 5 regions, but one of them's a lone pair, especially if you put it upwards, you can see that it's a little seesaw. I don't know who came up with some of these funny little names, right? But that's a seesaw. You probably didn't even know how to spell seesaw. I didn't until I got into chemistry. Now again, I've got lone pairs off of the central atom. That's what matters. And in this one, it looks like a letter in the alphabet if you turn it sideways. I know like that it doesn't look like it, but if you turn it like that, then you can see that it's a letter T. So that one is T-shaped. And now this one, sometimes folks have a hard time seeing this. So you've got a triangle of basically lone pairs. So the instruments don't pick that up, but they in fact are holding this this atom kind of captive apart from each other, and they actually are making a 180-degree angle, and so the molecular geometry here is going to be linear. Now I want a little note here, since we know in this case that we don't have, with our angles, we're going to go up to an earlier one too, we actually don't have the 120 anymore because we've lost our whole triangle. And we don't have the 90 anymore either because we've lost, you know, that halfway at the element that was halfway through it. So if I go up to here, notice that I've lost my triangle. I don't have that because I've got the lone pairs. So I don't have the 120, and I do have the 90, and I do have the 180. Like that, there, okay. Now I'm going to go up one more level for my angles. So I still have my triangle. You might not be able to see the triangle. This triangle happens to be like that. So I still do have that triangle. Making sure I'm said that right here. Yeah, I didn't have the 120. But up here I still have my triangle. And so that's 120. And then I also have the 90 and the 180 also. And then finally, on this one, there's no lone pairs to distort anything. All right, so now I'm going to move on to the octahedral shapes. So right here, again, without any lone pairs, then the octahedral shape is still just an octahedral. Octahedral, or non-bonding pairs, if you want to call them that. Now we've got a lone pair right here. And so the shape this ends up being, you've got a square right here, and you're going up, and it's a pyramid. So that square pyramid, square, base, pyramidal. We still have all of our angles. These two right here are 180 apart, and these two are 180 apart because it was a square. It may have looked like a rectangle to you, but it was supposed to be a square. And then on this one, the molecular geometry, this is your square, but there's nothing above and below. So this is just square, planar. And the bond angles are still there, the 90 and the 180, because again, these are 90 degrees apart from each other. So there's like 90 between there and 180 between there.